Just don't look. Yeah.
Hi, everybody.
Hi.
Kind of a low turnout today. I wonder why. It's not like it's a gorgeous day out there. It's all right, I guess. It's cold. But this is an important chapter that we just barely started last time. And it's our thermochemistry chapter. And it's going to be on the test. We have a test a week from Thursday. Sorry to bring that up. I know. Well, it's not really like you just had one. It was more than two. So exam 2 is November 2nd. And it's a Thursday next week. And one of the chapters that is going to be on this test is what we're covering this week in thermochemistry. So I'm sorry to see so many empty seats, but that's the way it is. Let's see. By the way, I'm going to have the homework. So the homework for chapter 4, part 2, I extended to tomorrow. But that's it. Then I'm cutting it off because you really need to work on the homework for chapter 5, which will be up right after class today. But, you won't be able to necessarily do a whole lot of it. Well, you should be able to do some of it at the end of class today. Okay, so that's new. And I want to, I did a bunch of introductory kind of talking last time about thermochemistry. So thermochemistry is really about where's the energy going in chemical reactions. Okay, so thermochemistry is about energy. It's about energy flow. Where does the energy go in chemical reactions? And this chapter is really all about how some reactions give off heat because they start at a higher energy and end up at a lower energy. And because of conservation of energy is never it's not created or destroyed. So that energy is not lost. It is simply released as heat into the environment. Okay, so when you have a reaction that starts off at a high energy, I'm a little earlier, okay, and goes to a lower energy, heat will be given off. So I gave the example. So that means if you start off with something, if this is energy here, we call this internal energy. And you start off with reactants at a higher energy. When they go to a lower energy, so this is lower internal energy, this is higher energy, U is internal energy, okay? Then at this case, what would happen? You start off at a higher energy, you go to a lower energy. So the system has less energy than it had before. Where did that energy go? Does anybody remember where the energy goes? It gets released, okay? So energy is released as heat, and we call heat Q. And we say that this is an exothermic reaction. That is when energy or heat is released, okay? So some reactions release heat, okay? And other reactions go the other way. You have a question? Because I didn't hear it. So other reactions will go from a lower energy to a higher energy. And in order for that's an uphill process. And for that to happen, would have to be supplied with heat. So heat is absorbed by those, we call it the system, but the system is simply the reacting chemicals, okay? So heat is absorbed here. We call this endothermic, where heat is absorbed. That's what that means, okay? And the products are at a higher energy. Now, the reason why some reactions are uphill, like this one down here, and some reactions are downhill, has to do with what is actually going on with the bonds in that reaction. The making and the breaking of bonds during a chemical reaction is largely responsible for what the change in internal energy is in a particular reaction. So I went through, I just, talked very generally about a couple of reactions that release heat that we use for energy, basically. And the two reactions that I talked about were, so if we have octane and oxygen, octane is an ingredient of gasoline, as you probably know. And the products, what are the products of that reaction? Anybody? CO2 and water, yeah. And that's a very downhill reaction. This is what happens in a combustion engine, and lots of heat is released. This is Q flowing out of the system. Lots of heat is released. And the reason for that is because these molecules down here, the carbon dioxide and water, have more and or stronger bonds, and the octane and oxygen has fewer and or weaker bonds. So forming bonds makes the energy go downhill. It makes the product more stable. So the products are more stable. And that's because of the stronger bonds, or perhaps it's more bonds. I think it's some combination of both. The other reaction I talked about was glucose and oxygen, also forming carbon dioxide and water. And this is the process, we know this as cellular respiration in the body. And this is also a downhill reaction because you have more stronger bonds in the products than you have in the reactants. So we also have a lot of heat released. So if we were, but in the body, what that energy actually, I should say energy released, because in the body, that energy is not released all as heat. Anybody know what that energy released is used to do? Maybe from your biology courses. It's used to generate ATP. And ATPs are used to perform all sorts of, as the energy source to perform bodily functions. So it's the energy source for cells. Okay, so all of this happens because these particular reactions are very downhill reactions, ending up with a more stable situation with stronger bonds than what we started with. So these are sort of complicated reactions, but I want to start simple. I mean, it's a little too much to start with these more complicated situations. So I just want to kind of start it a little simpler. So sort of take a step back and talk about, very simple reactions, how bonding stabilizes atoms. Okay, so that means that forming a bond lowers the energy of these chemicals, and breaking a bond requires energy, which is what is shown in these two short little slides. It's very distracting to have people coming in late. Try to come a little earlier. It's anyway, whatever. I mean, I know everyone has their own problems with getting here, but just give me a break, okay? All right. So anyway, here we have an uphill situation because here we have bonded atoms, and it requires energy. There's an energy input here. Energy is required to now break that bond. okay? That's an endothermic, which means energy is required, heat is required. And in this case, this shows where you start at a more stable situation. This is energy over here, by the way. This is internal energy on this axis here. And so you start out more stable at a lower energy and you end up less stable at a higher energy. Okay, and this is just a reverse process. If you take two atoms and form a bond that releases energy, this is an exothermic process. And the bonded atoms are more stable. So basically, that gives you a very simple illustration where you definitely have more and stronger bonds in the second picture, in the lower energy, okay, because it has a bond, and the ones on the left don't have a bond. So that's basically the simplest case you'll ever see. Now, this is true for any diatomic. This is true for any bond that is made. So it is true for hydrogens. It's true for oxygens. If I have two separated hydrogen atoms, that's at a higher energy than bonded hydrogen atoms. The same is true for oxygen. But you'll notice I drew the diagrams a little bit differently because the difference in energy between the separated atoms and the bonded atoms is different for H2 and for O2 because the bond strength is different. And there's actually a stronger bond in O2 than in H2. But what you could see here, and this is another way we illustrate this all the time, is we draw two levels, right? We draw a level up here for, hydrogen separated have a higher energy. So it's up higher and higher internal energy. And this is lower internal energy. If we're talking about going from two separated atoms, so we always start to draw an arrow, we start at the reactants. If we're talking about the 2H goes to H2 reaction, then that corresponds to this arrow, okay? But if we're talking about H2 goes to 2H, then we're talking about this arrow, all right? So this reaction here requires energy, and this one here releases energy, okay? And the difference in energy, we call this the delta U, because this is so we have, this is, if we're talking about, let's say, the 2H goes to H2 reaction, you can see that's the one that corresponds to this arrow right here, the second one. That's a downhill reaction. This releases energy. You could see that the final energy, so I'm only talking about for this one, here's the final energy for that one, and here's the initial, right? So what is the sign of the change in energy? So if we take the final minus the initial, we call that the change in internal energy. For this reaction, where energy is released, you end up at a lower energy than where you started. If you subtract a lower number from a higher number, you get a negative number, right? So this is going to be negative. But the delta U for the other reaction, H2 goes to 2H, that requires energy. That's this one here, this arrow going up. The delta U is UF minus UI. So now this changes here. This becomes UI and UF. Now the final energy is higher than the initial energy. And so this difference is positive. You're subtracting a smaller number from a larger number. So we say that delta U is positive when energy is required, and delta U is negative when energy is released. Does that make sense? And I could draw the same picture down here, okay? So UI and UF, are different depending on which way the reaction is going. Okay, so we've just figured out that separated atoms are higher in energy than when the atoms are bonded together. So if I had 4 hydrogen atoms and 2 oxygen atoms, and I went to 2 hydrogen molecules, here's my 2 hydrogen molecules, and 1 oxygen molecule, it stands to reason that this is going to be a downhill process. If we had 4 H's, here's the reaction written here, but I'll write it again. 4H plus 2O goes to 2H2 plus O2. That's an arrow. The arrow is going to point down. We're going from a less stable situation to a more stable situation. This would be your initial and your final. Your final energy is lower than your initial. So when you subtract, U final minus U initial, here, U final is less than U initial. So delta U is negative. Heat is released. It's exothermic. Okay. So if we have these 4 hydrogen atoms and 2 oxygen atoms, or 2 H2 molecules and 2 O2s, is there something else that we could do with those components? Is there another thing we could make from hydrogens and oxygens like this? If I have 2 H2 and O2, what else could that form? Yeah, H2O, 2 of them, okay? So this is a reaction that we're kind of familiar with. It could form water. So my question is, if we go from 2H2 and O2 to 2H2O, is this uphill or downhill? Will energy be required or will energy be released? Don't answer that question. Because I'm going to show you a video. You know, I try to record every single time. Sometimes it says record to the cloud. Sometimes it doesn't. And I wonder if it doesn't work when it doesn't say that. I don't know. I try every time. I really do. I'm very good about it. And I'm recording it now. If I go back here and I look more, see, pause recording, stop recording. So I'm definitely recording. All right, so let's try doing this now. See if this works. Now we have to watch the ads first,
what
I'm
keeps
afraid.
people who are about to retire up at night?
Oh, shut up.
The thought of having to
Today we're testing a few little things out, mainly in the theatre with the help of a little bit of hydrogen down here, which should be quite fun.
So what this guy is doing is he's doing the reaction that we're talking about, hydrogen and oxygen. Guys have a good time with blowing things up. Have a high enough ceiling.
Nice. Right, we do a really big boy now. There's still quite a lot of nitrogen left.
All right, let's do a big one.
Better, guys. All right, that's it. I don't know if that recorded, but whatever. I don't know if I shared that, but whatever. People could just click on it if they want to see it. Anyway, it's just exploding balloons. So, all right. So we just watched that reaction. Okay, tiny little spark and a huge fireball. Okay. Oh, I think it's still running in the background, right? It's probably somebody. Okay, killed that. All right. So we just watched this reaction. 2H2 plus O2 goes to 2. Now, those were hydrogen balloons, right? Where did the oxygen come from? There. Yeah. Okay. So when this was done, it was basically an explosion, right? And there's lots of heat, some light too. There was a tiny little spark that was required to get the reaction going. But once that reaction goes, it releases a ton of heat. And so I got to get, yeah, okay, just a minute. I want to get rid of this thing. I got to get rid of it.
Today we're testing a few little things out, mainly in the
Can I just get rid of this? My fantasy that it's gone now. Oh, damn it. All right, I'm just gonna have to ignore it. All right, so we had a big explosion, blah, blah, blah. So this reaction is definitely downhill. So if we go over here and I try to sort of line up how you can have 4 hydrogen atoms and 2 oxygen atoms. You can have them as separated atoms. You can have them as H2 and O2 molecules, or they could be in the form of water. If we line them up in terms of their energy, their internal energy, we know already that that's a downhill process, that releases energy. And obviously, looking at that explosion, how you get this huge release of heat and even light as you go from hydrogen and oxygen molecules to liquid water. You know that this is a downhill process. Now, you asked me, where's the water? Okay, so this is what I'm going to say. When this reaction is happening and there's all that heat, I am sure that water is generated in the gas phase because it's just probably above 100 degrees C, which is the boiling point of water. Okay, but when the whole area cools down to room temperature again, there's going to be some water droplets somewhere in the room. It's definitely going to become a liquid again once the temperature is no longer high, once the heat dissipates and it goes back to normal room temperature. Okay, so what I want to talk about now is why is water lower in energy? So let's look at this. Let me just draw this reaction again. 2H2 plus O2 goes to 2H2O. And now I'm going to show you that hydrogen, we have 2 hydrogens. You have 2 HH bonds. You have 1 OO bond. And then on this side, we have 2 molecules of H2O. So let's just look at the bonds here, because that's going to tell us everything. Okay, so what you see here is that you have 4 OH bonds on the right. On the left, you have 2 hydrogen bonds and 1 OO. So already you could see that you have more bonds here, right, than you have here. Remember, forming bonds is what releases energy. Now, it's true that not all bonds are alike, okay? Hydrogen bonds with other hydrogens are kind of weaker bonds. An OO bond is stronger. But here you have 4 strong OH bonds. And that ends up releasing energy because you have an extra bond, and the OO bond, while it's a little stronger than an OH, the OHs are much stronger than the HH. You don't have to write that stuff down. I'm just telling you that. That's really a topic for Chem 104. Yeah. It's because the atoms are smaller. There isn't as good of overlap. There's not as many electrons when they overlap to form a bond as there is in O2. O2 is actually a double bond, which we learn about later in the semester. And anyway, so that's I guess that's one reason anyway. Okay, so we know that energy is released here, that the delta U, because you're going from a higher energy to a lower energy, the delta U, what is the sign of that delta U going to be? Here's U. Okay, here's our final, U initial. Oops. So delta U is always the energy of the final state minus the energy initially. The initial is higher. You subtract a higher number from a smaller number, it's going to be negative, which we call, as I've said, exothermic. So energy is released. And now, yes. Never mind, right? It's 4 H atoms, but it's 2 H2 molecules, right? That's balance. Okay, and this brings us to what is known as the first law of thermodynamics, first law of TD. And what the first law does is it gives us a way of keeping track of the energy changes in a reacting system. So when you have a chemical reaction and you have a change in internal energy, it tells you where does that energy go, because energy cannot be created or destroyed. So what the first law does is it really gives us a way, it keeps track of the energy changes in a reacting system. And it says that the change in internal energy is the sum of the heat transferred and the work done. And we write it, delta U is Q plus W, where this is heat and this is work. Okay, so in the hydrogen fireball example, in the reaction that we just looked at, the internal energy drops. We know that a lot of heat was released. But what about work? Okay, so we do have to worry about this a little bit. So lots of heat was released in the reaction. But what about work? Okay, well, was any work done? Well, what is work? What are we actually looking for? Okay, so we really have to think about this a little bit. A system, or does work when when a mass is being pushed or a mass is being pulled, when you have a force that's pushing over a distance. In fact, work in its simplest definition is force times distance. So it's when there's pushing or pulling involved. Well, forces involves accelerations. You have to accelerate the mass. It's stopped. It's not moving. Now it's moving. So that's definitely an acceleration because it went from 0 to whatever. Okay. So there's pushing or pulling involved. So my question is there pushing and pulling involved in this reaction? And the answer is yes, but it's not particularly obvious, and it's not a particularly big deal either. But the truth is that yes, something is being pushed here in this reaction. So what? Okay, so I'm just going to draw you kind of a sketch, a stupid little picture, really. If we start, here's the before picture. Before reaction, we have 2 moles. Let's say we have 2 moles of hydrogen gas. Okay, 2 moles would be about 44 liters of hydrogen gas. So that's kind of maybe what the big balloon was. Okay, I don't know. And 1 mole of oxygen gas. Okay, that's the before. After, And now what I'm talking at 25 degrees C, let's say, that's room temperature in Celsius. After, of course, you get this big fireball, but let's let the temperature of the room return back to 25 degrees C. Okay, so we're back to 25 degrees C. So now all the water that was generated is now liquid water, and we have 2 moles of liquid water. So here's the picture. Before the reaction, you have like this giant volume of gases. You have a large volume. And after reaction, you have a few drops of water. So what is being pushed in a way? So you have the atmosphere, which is pushing in all directions. So the atmosphere is pushing on this volume. And then and what happens is it ends up smaller. So effectively, by the fact that the system compressed, it meant that some work was being done on that system. Okay. It was actually, the volume was getting bigger initially, but then it ended up as a few drops of water. And all we care about is the initial and the final. And from the point of view of, whether the system was expanded or compressed, it actually compressed here. So the system is compressed. And so the atmosphere was pushing the system. It did work on the system, we say, in the language of thermodynamics, which is a little bit cryptic, but still, the system is compressed. And so that means there was pushing, and it didn't move a distance because it's a small drops now. So this is work. And I will never ask you to calculate work from this. The book spends more time on this than I would ever spend, because I don't think this is important, which I'll tell you about in a minute. But anyway, because the first law includes that W, we have to include it. Delta U is Q plus W. So this really has to be accounted for if we're going to get right answers, right? We don't want to get wrong answers. But let me give you an idea of the numbers here. So for the reaction, 2H2 plus O2 goes to 2H2O liquid. This Q for 2 moles of hydrogen forming 2 moles of water, okay? This Q is minus 570 kilojoules, okay? This work is 7.5 kilojoules. Okay, so you could see that you have a very small contribution from the work. And us chemists, we would really prefer not to think about that, what we call expansion work or compression work. We don't want to think about that. We really are only interested in the Q. So chemists would prefer to leave out the W, okay? So chemists just don't care. Well, that's not true. They care in some contexts, but we really don't care right now about the W. So we would prefer to leave it out. But it's just not right to leave it out. So what did they do? They very cleverly came up with another energy, another not internal energy, U. They came up with something called enthalpy. And it turns out that if the atmospheric pressure is constant, the enthalpy is just the Q part. It's just the Q part. So whereas we had delta U is Q plus W, now we have a new energy, which we call enthalpy. And enthalpy has the symbol H. And delta H, the change in enthalpy, is just the Q part, as long as the pressure of the atmosphere is constant. And what reactions do chemists care about? we mainly care about reactions that occur on the bench top. The bench top is under atmospheric pressure, and so the pressure is constant. It's whatever the atmospheric pressure is. So as long as we say that the pressure is constant, we can simply use this equation here. So that I'm not going to put U's on diagrams anymore. I'm not talking about internal energy anymore. I'm talking about something called enthalpy, which is very much like internal energy. The change in enthalpy also depends on the bonds that are broken and the bonds that are formed. It's just that we don't have to worry about the work. And I think you should skip the whole section in the book about, enthalpy and work. Well, not about enthalpy, but about the, how the difference between delta U and delta H. Just think about it, that delta U and delta H are the same, except for the work, which is generally pretty small, and that this is exact as long as the pressure is constant, which it is in, benchtop reactions. So this is what we chemists tend to use.
So the delta U would be used for, I don't know, outer space stuff.
Oh, no. Delta U is used. Delta U's, like if you did a reaction at constant volume, if it wasn't at constant pressure, then you would use delta U. There's lots of, if you're majoring chemistry and you take physical chemistry, you'll do many problems on the difference between delta U and delta H in given reactions. But for general chemistry, there's no need to complicate the issue. We are talking about the heat. The heat released or absorbed is delta U as long as the pressure is constant. And we could think about the change in enthalpy as being due to bonds breaking and bonds forming, just like it is with internal energy. So, and changes in delta H, just like delta U, are largely due to bonds breaking and bonds forming. Bonds breaking, which requires energy, and bonds forming, which releases energy. Change in. Okay.
Could you show us a problem of like how this would come up on a test? Like what is it that we need to?
I'm going to show you a million problems. Okay, so just to sort of summarize, and then I'm going to introduce another aspect of this. We have this reaction, which I've drawn this a million times already, 2H2, but I'm going to add something else. Here we have our reaction. Instead of putting a U, I'm going to put an H there because we're only worrying about the Q. Okay. These are the reactants and these are the products. And so we always draw the arrow from reactants to products. We have that heat is released. This Q is equal to the delta H, which is negative because here's our final and here's our initial. So delta H is H final minus H initial, and the final is lower than the initial. So when we subtract a larger number from a smaller number, we get something negative. Okay, so this is all just kind of what I did for delta U before. It means that the products have stronger or more bonds than the reactants, just like when we talked about delta U. Okay, now a lot of times this type of information, so a lot of times this the type of, and also I want to give you what this delta H is. Okay, and for this reaction it's minus 570 kilojoules, and that's So that allows us to write something called a thermochemical equation, which is just like our chemical reaction, except in addition to writing what the reactants are and what the products are and what the phases are, we put a little semicolon and we put what the delta H is for that reaction, which is how much heat is absorbed or released. So we would write it 2H2 gas plus 1 O2 goes to 2H2O semicolon, which didn't come out because my pen stopped writing. And then we say delta H equals minus 570 kilojoules. Now, it's important. Oh, go ahead. Question. Okay, you have enthalpy over here. Up here, this is a higher enthalpy value. This is a lower enthalpy value. Whenever you take a delta, that's the change in something. What that means is you take the final value minus the initial value. But the final value is lower. Let's say the final value is 3 and the initial value is 10. I mean, these are ridiculous numbers, but that's okay. It illustrates, okay? So now if I take 3 minus 10, it gives me a negative number, right? Because it's up and down. The upper is higher. Lower is the higher energy is further up. Lower energy is further down. So that would mean, okay, that would be going the other way. That would be if you were going from 2 waters to H2. Then the HI and HF would flip, right? That would correspond to a different reaction. So here, for the red, this would be HF and this would be HI. And then the final would be higher than the initial, and that would be positive because you'd be subtracting a smaller number from a bigger number. Energy. Yeah. Okay. So it's important to realize that this minus 570 here, the negative is for the fact that heat is released in this direction, right? This corresponds to however many moles are in this equation. So in other words, it would be negative 570 kilojoules per 2 moles of H2 that react, or negative 570 kilojoules per 1 mole of O2 that reacts, or negative 570 kilojoules per 2 moles of H2O that form. Okay, so this number here in the thermochemical equation corresponds to the stoichiometric coefficients as written. Okay, it's not arbitrary at all. It has to correspond to a particular amount. So the delta H depends on amount. If it didn't depend on amount, I wouldn't have to bother writing how many moles it refers to. Okay, so this is an example, at least the black. The red is I added on later. I really want to erase it because I don't want to confuse it, but oops, that wasn't so good. Okay, that's an example of an exothermic reaction where heat is released. I want to give you a similar example, but with an endothermic reaction. So here's a reaction. Here's another example for an endothermic reaction. An endo, again, means requires heat or absorbs heat. So here is a reaction. Oops, not. This is N2O4. Okay, so we have N2O4 gas goes to NO2. Okay, so you have these two. So let me ask you, why do you think this reaction is endothermic? Why does this require heat? What is happening in this reaction? Yeah, basically all that's happening is that one bond breaks. Breaking bonds in general requires energy. Okay, so I know this is going to be endothermic. So the diagram for it would look like this. So what would go, all right, the reactants are N2O4. Yeah, this is going to be my N2O4 over here. And it has to go uphill on the enthalpy scale to get to 2NO2. So now our final is higher than the initial. So the delta H, the change, which is the final minus the initial, is a larger number minus a smaller number. So it is, what's the sign? Positive, right? So delta H is positive, it's endothermic. Okay, so heat is absorbed, or heat is required, or heat is absorbed. Delta H is positive. And the reason for this is that the products have fewer bonds. So we had a net breaking of a bond, which requires energy. So I could write the thermochemical equation for this reaction. And all it needs is for me to put down the value of the delta H, which is the amount of heat absorbed. And that number is 55.3 kilojoules. So that means 55.3 kilojoules per 1 mole of N2O4 reacting, or per 2 moles of NO2 forming.
Is the purpose of this find the kilojoule, or is the purpose of this to know if energy is being released or if it's being absorbed?
Well, right now there isn't a purpose because I'm not asking you to figure anything out. But we will be doing that very soon. And we'll be using these as dimensional analysis factors, as equivalence ratios for figuring out if you're given an amount reacting, how do you figure out the amount of heat? If you're given, that's a purpose. So I'm going to go through that now. I didn't tell you I wasn't going to do it. In fact, right now, here we go. So come on, guys. This is not limiting reactants. Of course, yeah. Well, that's one of the reasons. Okay, so we have this reaction, and we know the delta H is 55.3 kilojoules. So now I ask, so what if 4 moles of N2O4 react? Okay, so this is a typical chemistry problem where you start with what you know. Start with what you know. 4 moles of N2O4. And now, because I have this thermochemical equation, I have relationships like this, which tell me how energy relates to amount of N2O4 in moles. So I can use this guy, 55.3 kilojoules per 1 mole of N2O4. And you could see that we can do what we normally do. We get rid of the moles of N2O4, and we end up with 221 kilojoules as the delta H. So that's the delta H for 4 moles of N2O4 reacting. Okay, and you'll notice it's 4 times what it was for 1 mole of N2O4 reacting. That's because the delta H depends on amount. You can imagine if you had hydrogen and oxygen reacting and you doubled the amount of hydrogen gas, made the balloon twice as big, you have twice as much heat released. So that's an important thing to realize. Delta H depends on amount. On amount reacting. Yeah, I looked it up in a chart of enthalpies. Yeah, there's many ways to do it. Okay, so 4 times as much N2O4 reacted, 4 times as much. So I had 4 times as much heat absorbed. Okay, so what if 5 moles of NO2 form? So you guys, what do I do here? What if 5 moles of NO2 form? Well, I start with what I know. 5 moles of NO2. And now, instead of using this guy, I have to go back and say, oh, there's a 2 here. So that's 55.3 kilojoules per 2 moles of NO2, as I wrote over here. Because there's a 2 in the equation that has this 55.3. It has 2 moles of NO2. So it's 55.3 kilojoules per 2 moles of NO2. And when you do that, it comes out to 138 kilojoules of heat would be required for 5 moles of NO2 to form. Okay, so now let's just take out activity 1 that you have in the packet that I gave out. If you were here on Thursday, you have it. But if you don't have it, take it. Anybody need this handout from last time? Anybody need the other handout? Maybe. Sorry. Really? Yeah. Oh no. I forgot to put that page in. Oh well, you have to copy the problem. That's life. I'm really disgusted with myself. I had to actually staple every one of these because the copier didn't have staples. But then I screwed up, right? Imagine if I was teaching full-time. Really a mess. Okay, you might as well copy B while you're at it, because I'm going to ask you guys to do these problems, okay? I'd run up to biology, but I don't even have a copy, a blind copy. I forget activity 1, honestly.
You post the.
Yes, I'm going to post it.
Yeah, I mean, like when you make packages, can you post
I always post it.
You post it before? Or?
I probably post it today. I always post it.
Like we can print it ourselves.
Yeah, no, I post all the activities, but I didn't do it yet. I was too busy writing the homework, writing the quizzes and all that crap. So you start, don't forget, you start with what you know. And then you put in here, you know, what's going to go in there. Don't forget there's not a mole ratio. What? So what do I write down here? 1 mole and 204. And what do I put on top? That's right. Okay. So this is just like what I did for 4 moles. And then you have to ask yourself, is heat released or is heat absorbed? Since this sign is positive, it means heat was absorbed or required. Okay. And now this one, what do I have to do before I do something like this for this problem? I'm going to, you have to get the moles. So let me tell you what the molar mass of N2O4 is, because I don't want you to have to go through that trouble. It's 92.02 grams per mole for N2O4. Did you get the moles? What'd you get? Anybody? I'll let you have a few more minutes. And then I'll show you the next one. I did it wrong. No one's even telling me. Wait. Oh, I guess I didn't do it wrong. I just wrote it wrong here. Oh, no. Oh, no, it's right. 1 mole. Sorry? Yeah. Sorry. So when you do this, you get the moles. You get 0.190. And now you start with that, or you could just keep going in a continuous, use of these parentheses. So we know it's 55.3 kilojoules per 1 mole. Oh. We got the grams, we got the moles N2O4. Now we're using the moles of N2O4 to get the energy. So this part here is just like what we did up here. So is everyone following me? Anyone have a question about this? So yes. I always do, but it didn't work last time. I try every single time.
I need this recording.
You know what? I got to tell you, people, I love you all, and I want you to walk out of here understanding everything. But that's not the way it works. You have to go home and you have to study it. And it's hard. And when I saw this for the first time, I didn't quite get it in the classroom either. So you just have to put in the time. And I have an office across the campus, and I am there for hours, and nobody shows up most of the time. Oh, bull, come on. It's dark and scary at 2 o'clock in the afternoon on a Wednesday. So, you know, you have to seek help if you're not getting it, you know. So anyway, but this is exactly what we did before. You know, did you understand this part here? We're figuring out how many moles of a reactant. We know that per mole of reactant, we have this much heat. And the only difference with this problem is we started with grams, and you've been converting grams to moles for weeks now. So that shouldn't be too bad. So now we have a moles, and now we are taking that number of moles. I'll write it a little neater. I know it's a little bit squeezed. That must be the problem. Okay. And now again, we're multiplying it by the heat absorbed per mole of N2O4, and we get 10.5 kilojoules. And that's heat required because it's positive. Okay. So now we have, now this is a little bit different. Okay. So suppose that 261 kilojoules of heat is absorbed when this same reaction happens. So how much must have reacted? So now we're going from the amount of heat absorbed to the amount that must have reacted. So again, you start with what you know, what you're given. There's what you're given, okay? Now, how am I going to use this to get to moles of N2O4? So you could see that I'm going to have to get rid of kilojoules. That's going to have to cancel. And I'm going to have moles of N2O4 here. So let's look at that reaction again. Here it is. N2O4 goes to 2NO2. Okay, so I'm looking at my thermochemical equation. And so now I'm going to use this 55.3 kilojoules per 1 mole of N2O4. And notice that this is flipped from the way I used it before. Right? Before I used 55.3 kilojoules per 1 mole of N2O4 with the 55 on top. Now the 55 is on the bottom. But it's the same, we call it like it's the same conversion factor or the same equivalence ratio, that 55.3 kilojoules goes with 1 mole of N2O4. So when I do this now, I'm dividing by the 55.3, and it ends up as 9.43 moles of N2O4, doesn't it? Oh, who got the gotcha there? You? All right. You have to come and see me for that gotcha, you know, otherwise I forget and I'm not going to give it to you too late. So come and get them. All right. So that then, the moles to grams is something you already know. That's 92.02 grams per 1 mole. And so that comes out to 434 grams of N2O4 reacted. Wait, yeah. Okay. And then it also asks how much NO2 formed. So I'm going to give you a chance to get a special problem on that for next time. Okay, so I want to show you that there are different types of enthalpy problems to do, and I don't want you to be confused about it. So I actually, in this packet, I managed to include a piece of paper that says summary of different types of enthalpy problems. Okay, so it's the second page. And what we have just done is what I call a type 3 and a type 4 problem. Okay, so I just want to point this out so you can go and read about it. But basically a type 3 problem is when you're given a thermochemical equation, okay, and you determine the amount of heat when a certain amount of reactant reacts. That's called a type 3 problem. A type 4 problem is when you figure out how much reactant reacted or how much product formed when you're given a certain amount of heat that reacts. So you could go and look at these. and compare it to the problems that we just did. And maybe it helps you that I have this compilation of the types of enthalpy problems. I hope so. That's why I do it. So, so I want to move on now to this. Okay, so here I'm going to give you a chance to write this down because I know you don't have it. But basically, we're trying to find what would the thermochemical equation be for the red reaction, which is very closely related to the one we've been working with. And also this reaction. So those are the next two things we're going to investigate. Sometimes you have to calculate it, but we haven't gotten up to that yet. There are ways of calculating it. Yeah, that's the change in enthalpy. That's that funny energy that is the Q in the first law. So in other words, delta H is the Q part of the first law. You know, delta U is Q plus W. We can ignore the W as long as the pressure is constant. That's the heat. That's the delta H. The delta H is the heat part of the first law. Don't worry about the W because we don't have to. The pressure is constant. Enthalpy is related to internal energy. I probably should give you the definition, but I don't think any of you really will care. H is actually defined as U plus PV. Boy, that sure illuminates a whole lot of nothing if you ask me, but that's its definition. And if you take P-Chem, we talk about it for a long time, but it's really not necessary to go on and on about that in Gen Chem because really it's not going to help. Sorry? Pressure times volume. Yeah.
And U is internal.
That's right. H is U plus PV. No, it's just whatever it is. What? All right. So what do you think about this? We've been talking about this first equation here. The one with the 1 N2O4, right? That's a 1 there. So what do you think is the thermochemical equation for this? So if I write this down, what would my delta H be here? And how did you get that? Yeah, I will multiply the 55.3 for 1 N2O4 by 3. Okay. So for this reaction, it would be 3 times 55.3, or as Nikolai said, 165. Is that what you got? Kilojoules. So that would be because we had 1 N2O4 goes to 2 NO2, and you have to multiply by 3 to get the 3. So we have to multiply the delta H by 3 as well. So because delta H depends on amount, if you have an amount and you know what the delta H is and you multiply that amount by 3, you're going to have to multiply the heat by 3 as well. Okay? And this is just delta H depends on amount. If we take 1 mole and we make it 3 moles, N2O4, we have the 55.3 goes to 3 times 55.3 kilojoules as the delta H. I just rewrote just what I just said, okay? What about this? What's going on here? How is the red boxed equation related to the first equation? It's the reverse. It's a reverse reaction. So remember, we had N2O4 going to 2 NO2, and it was uphill, right? That way. So when you go the other way, What is different about the sign of delta H here? Right. Here it's negative. The other way, it's positive. So when you reverse an equation, the sign of the delta H changes. It goes from positive to negative or negative to positive. So for this one, I'm just going to put my colon here. Well, I might as well just, I'm trying to be quick, but it's not working. So 2NO2 goes to 1N2O4. Delta H is negative 55.3. So that would be corresponding to that reaction here. It would be exothermic, whereas the other reaction, use black to keep color coded here, I guess, would be endothermic. Okay, so reverse a reaction, change the sign of the delta H. Yeah. Okay. All right. So the next thing I'd like to talk about is how can you tell in the lab by observation, how can you tell whether a reaction absorbs or releases heat? Yeah. I suppose if you see a flame and burning, but most of the time we don't, you know, especially in the lab, we don't like to generate too many flames. You know, it's kind of frowned upon by the powers that be at the college and stuff like that. So suppose you have a reaction in a test tube, which is much more likely. Okay, now I want to say that we talk a lot about this thing called the system. And I want to make it clear that what the system is the reacting chemicals. Okay? That the solvent is actually not part of the system. It's part of what we call the surroundings. The surroundings is really everything else. But we don't care about everything else. We don't care about the moon and about, you know, Melissa sitting over there in a chair when the test tube is over here. There are certain things that we care about in the surroundings. Okay, like the solvent, the test tube, and in many cases, the atmosphere that is close by. Okay, so if we have a reaction in a test tube, my system is definitely inside the test tube as the reacting chemicals. But so is the solvent in there, actually. So if this reaction is exothermic, so let's first consider if we have an exothermic reaction. What does it mean, exothermic? What's happening? Heat is released. So this reaction is releasing heat. Where is the heat going to go? It goes from the system to the surroundings. So it heats up the glass, it heats up the solvent, right? Even if it's an aqueous solution, it heats up the water. The heat flows from the system to the surroundings. So it heats up the solvent, heats up the glass of the test tube. It heats up the air around it. It heats up your hand if you're holding it, right? It feels hot. So when you have an exothermic reaction, it feels hot. No, it feels cold if it's endothermic. I'm going to do that next. Okay? So that's the exothermic example. But you can also have the opposite case, where you have endothermic. So heat is absorbed. So again, you have your system, your reacting chemicals, and then you have your surroundings. So you have to think about if a reaction requires heat, and you're holding this test tube, where's the heat coming from? It comes from that's the only thing it can come from. There's nothing else. You have the system and you have the surroundings. So it's going to go this way. This arrow is the direction of the heat flow. So heat is flowing from the surroundings into the system. You're holding that test tube. You're part of the surroundings. It is taking your heat for that reaction to go on. Can you not interrupt me every sentence? If I'm holding ice cubes, the ice cubes will melt. They will supply the heat. So they will. No, that's the opposite. Now, if I'm holding water, it might turn into ice. Heat is coming out of those, whatever it is that's in the surroundings. Okay, so here we have that the surroundings supplies the heat for the reaction. Okay, so that means that the surroundings will cool. As the heat flows into the system. Okay. There's a wonderful example of this, that if you took a shower this morning, you experienced it. How many of you took a shower this morning? Or last night? Yeah. I'm not looking. I don't care if you took a shower. But when you step out of the shower, do you feel nice and comfy? How hot is your bathroom? I mean, but you feel pretty cold when you step out of the shower, right? You feel cold. And why is that? That's because this is happening. The water on your skin is evaporating. This is endothermic. This requires heat. Where is the heat coming from? You are supplying that heat. And so, because it takes heat for water to go from liquid to gas, your body supplies this heat. And so you feel quite cold when you step out of the shower. Okay. All right. Now, changes in temperature when a reaction absorbs heat or releases heat can be used to figure out the Q, or the delta H. So you don't know how to measure a delta H, but you know how to measure a change in temperature. Okay, so changes in temperature when a reaction occurs allow us to figure out what the heat is. Which, in fact, since Q is equal to delta H at constant pressure, means we can calculate a delta H that way. Yeah. Oh, some reactions or processes don't require or release much heat. Like, for example, when you dissolve sodium chloride in water, I think that the delta H is 1 kilojoule per mole. So you wouldn't notice that if you just dissolved a little bit. You know, a lot of times, just not much heat. You can't tell, So there are a lot of reactions with relatively low magnitude delta H's. So no, it doesn't have to. No. Yeah, sure. Possible. Yeah. Anyway, so how do we relate changes in temperature to a Q? And this topic is called calorimetry. Calorimetry is where you relate the delta T to a Q. Okay, so you could have a reaction in something called a calorimeter. So here's kind of a calorimeter. You have a container and it's insulated. And in fact, we are going to use the classic calorimeter that's used in general chemistry labs all over the world in 2 weeks in lab. And it is a styrofoam cup, which is a little bit not that great because it doesn't have a cover. I mean, technically you should have an insulated cover on top of it. But what you would have and what you'll have in 2 weeks is you have a reaction sort of mixture in here. This is insulated. Of course, the styrofoam cup is, tiny, but it's good insulation, pretty good. And there's another thing that is needed in this picture, and that is a thermometer. So you'll have a thermometer here. And when the reaction occurs, so we have a reaction occurring here, and it is either going to absorb heat or release heat. Let's suppose it releases heat. Suppose heat is released. What is going to happen to the temperature in that thermometer when the heat is released? It's going to go up. Temperature is going to go up. Let me use my other pen here. Maybe it'll start here. It'll go up. You see what I'm doing? I'm making like the mercury going up or the alcohol or whatever's in the thermometer. T goes up. And that's for an exothermic reaction because heat is being released. Okay, suppose heat is absorbed. Then what's going to happen to that thermometer? It's going to go down. So it's going to start here. It's going to go down to here. The magnitude of that change in temperature, so this is a delta T. Now, in the case here where the temperature goes up, the delta T is positive. Here, the delta T is negative. But the size of the delta T is related to how much heat was absorbed or released. Okay. So what you can do here, you have these reacting chemicals, the temperature goes, let's say it goes up. That change in temperature will be able to give you a heat, but not directly because the heat is actually only proportional to the change in temperature. It's actually equal to the mass multiplied by something called a specific heat. Sometimes it's called a specific heat capacity. I think our book just calls it specific heat times the change in temperature. Okay, so this is M. Now, mass of what? Well, it's the mass of the entire reaction mixture that's going up, and the heat that transfers from the reaction into the solution there and causes the temperature to go up. That heat can be gleaned, can be figured out from the change in temperature, but it needs to know these other quantities as well, because that affects the temperature rise. Yeah. Whether the reaction releases heat or absorbs heat. The temperature will go up. Yeah. So, delta H. But delta T would be. Yeah, I was going to get to that, but you're too smart. You brought it up too soon, but good. It's great. Really, I'm glad you noticed that. Yeah. So what's happening here? She actually accurately pointed out that if you have an exothermic reaction, don't forget that this is delta H. So if you have an exothermic reaction, delta T is positive, but delta H has to be negative because that's what exothermic means. Okay. And the reason why is a sign mismatch there is because this temperature rise is actually being measured in the surroundings, and the heat went from the system to the surroundings. So whatever heat left the system goes into the surroundings. And that's why we actually have to use, instead of MCS delta T, we have to use negative MCS delta T. And to make it be true that for an exothermic reaction, you know, you use a positive delta T, but you end up with a negative delta H. And vice versa. Okay. All right, before I get into heat capacity and everything, I want to spend a few minutes on temperature. By the way, I will not ask you to solve calorimetry problems for chemical reactions on a test or an exam. The reason I'm going through calorimetry is it's important, but also because you're going to be using it in lab in 2 weeks, and I don't want you to be lost. But I'm not going to actually ask you to solve a problem like the problem on this piece of paper here, which we're going to get to. All right, that's a little too complicated for Chem 103. So I'm not going to ask you to solve a problem like that, but you need to know it because you're going to do it in lab, and you need to know it there for that one example. And so anyway, but I want to go over something. We've been talking about change in temperature and all this stuff, and I don't even know where maybe you have learned about temperature scales. And, you know, we use the Celsius temperature scale most of the time in science, at least. Well, actually, we often use, well, let me just tell you about these 3 temperature scales, okay? So we have the scale that we use in the United States and in Britain and maybe Australia, but no, you know, basically the British Empire, and that's the Fahrenheit scale. And that's what our weather is in Fahrenheit and stuff like that. We know, like, for example, Fahrenheit, the boiling point of water is 212. So that's up here, BP of water. But it's 100 degrees C. And it's also, we have something called the Kelvin temperature scale. So we have Fahrenheit, Celsius, and Kelvin. And the boiling point is 100 degrees C. The melting point of water is 32 Fahrenheit or 0 degrees C. But there's some other temperatures that should be familiar to you, which I'd say room temperature, you probably should know just to be an educated person. In Fahrenheit, it's about 77. In Celsius, it's 25 degrees C. Now, of course, you could be saving on heat and your room temperature could be 68 degrees Fahrenheit, but room temperature, 25 degrees C is 77 Fahrenheit. What about body temperature? What is the body temperature in Fahrenheit? What is it in Celsius? What? 37, right? If you're 32, you're pretty bad. That's I don't know what's used in Australia. I figured it was kind of like Britain, so maybe they use. Oh, it does. That's embarrassing. Well, they must use it somewhere else, Kelvin, Fahrenheit. But anyway, all right. So here's the thing. If you look at these different temperatures, you have the boiling point and the freezing point. There is an 180-degree difference in Fahrenheit and a 100-degree difference between those 2 temperatures in Celsius. So it makes converting from degrees Fahrenheit to degrees Celsius, these conversions are hard. I will never ask you to do them. I really don't care about that. We work in Celsius in this class. And in Chem 104, we do another scale called Kelvin, which I have to tell you about. It's very easy to convert from, so what Kelvin is degrees C plus 273. Okay, so and so And so to go from C to Kelvin, you add 273 degrees Celsius is Kelvin minus 273. And why do we even have this Kelvin scale? And you could see right away over here, see where you have 0 Kelvin. 0 Kelvin is absolute zero. It doesn't get any colder. In fact, you can't even get to absolute zero, although they've come so close. They've come within like 10 to the minus 9th degrees of absolute zero, but they've never gotten there, and they've really tried hard. So we really do think that this is the coldest possible temperature. So in Celsius, you have to use, and Fahrenheit, you have to use negatives. But, you know, the Kelvin scale is considered the absolute temperature scale because it starts, its zero is actually as cold as it could possibly get. And so that is related to the Celsius scale in a very easy way. All you have to do is this adding of 273 or subtracting, but we don't use Kelvin in Chem 104 at all. So you don't even have to know that. But those are the 3 temperature scales. But in this classroom, we basically use degrees Celsius. Now, as a person living in the United States, you're used to degrees that are about half the size. So a Fahrenheit degree is actually a little bit more than half of the size of a Celsius degree. So you could see that between 32 and the freezing point and the boiling point, you have 180 degrees here, whereas it's only 100 degrees in Celsius. So it's there's a difference in degrees. But that really, I'm sure you're used to Celsius by now anyway, from work maybe you've actually done in labs before. Have we done anything where you've had to measure the temperature yet? Well, you're going to do one in 2 weeks, okay? So that's what we use. We use the Celsius temperature scale. Okay, so getting back to the fact that we have Q is equal to the mass times this specific heat or specific heat capacity times the change in temperature. And then we could use that Q is delta H because the temperature is constant. So let me sort of go over what it means, what specific heat is. So if we go down here, I gave you this piece of paper. And if you look over here, it actually tells you that the specific heat or the specific heat capacity is the amount of heat that is needed to change the temperature by 1 degree Celsius. To change the temperature of 1 gram of a substance by 1 degree C. Okay, so if you're heating up the substance, then the temperature change will be increasing by 1 degree C, you're heating it up. And so for water, you would need 4.184 joules per gram per degree C. So CS for water is 4.184 joules per gram degree C. You have to supply a really pretty large amount of heat to get water to raise its temperature by a degree. Okay, so this quantity, this specific heat, sort of tells the amount of heat that's required to change the temperature of that substance by a small amount. Yeah. Not to change the substance, to change it. Yeah. It would be absorbed if the temperature is going up. Yeah. It would be released if the temperature is going down. Required released when the temperature increases, decreases. So I'm taking all my bases are covered there. The released goes with decrease, the required goes with increase. Yeah. Requires the same as absorbed. So all right, so all substances have their own specific heats. This is because different substances handle heat differently. Okay, so if I put a bunch of heat into water, Water is very good at handling heat. It has a lot of places to put heat. But if I put heat into iron, there's really nothing the iron can do with it except for its atoms to vibrate in place wildly, which raises up the temperature. So these substances are really very different. And you could sort of compare the specific heats of different substances by doing something, it's almost like a touch test. So this is activity 2. And I want to do this, and I hope that it will help you understand heat capacity a little bit, or specific heat. So let's suppose we have the same size, the same mass of iron. Let's say we have 100 grams of iron, and we have 100 grams of water. Okay, and each of these starts at 25 degrees C. So that's the initial temperature. And now what I'm going to do, here's my iron block. I'm going to put heat into this, and I'm going to give it 23,000 joules of heat into this 100 grams of iron. And I'm going to do the same thing with my 100 grams of water. I'm going to put 23,000 joules. Okay. So here's the question. If you did this and I gave you $1,000 to stick your hand in one of these things, which one would you rather grab? The water. And that means that you know intuitively that that iron is going to heat up way more than the water is. And that's because iron has a much lower specific heat than water. Iron doesn't have anywhere to put that energy except for the temperature to go up. So let's just figure this out because it's kind of like amazing, okay? So Q is the mass times the specific heat capacity times delta T. So if I know Q and I know M and I know CS, what I'm solving for is the change in temperature. That's what I'm really figuring out, is what is the final temperature? So what I need to do is I need to get the change in temperature and then add the initial temperature, because TF minus TI is delta T, right? So T final is delta T plus T initial. So let's get this delta T for the iron. So Q is 23,000. The mass we know is 100 grams. So what is CS for iron? So if you look on the chart here, it tells you that it's 0.450, and that's joules per gram degree C. So I'm going to take the Q and divide it by the mass times the specific heat. That's 23,000 joules over 100 grams. This is going to give me my delta T, right? So if I solve for delta T, it's Q over MCS is delta T. And this is 0.450. And this comes out to a whopping 511 degrees C. So if I started, that's my delta T. So if I started at 25 degrees C as my initial temperature, and the change is 511, what's my final temperature going to be? I have to add these. So that's why you don't want to touch it. Well, what about if you do the same thing with water?
When you say that the step for iron is 0.450, that's 0.450 what?
Joules per gram degree C. Per gram degree C, yeah. So here I'm going to do the exact same calculation. I'm going to take Q over MCS, and that's going to give me my delta T. And it's the same calculation, except, and I even have the same grams, except instead of this number, it's 4.184 joules per gram degrees C. And that comes out to 55 as your delta T. So the final temperature is the change in temperature plus the initial, which was 25. So that's 80 degrees C. I find that kind of astonishing, really. You could put the same amount of heat into 100 grams of water. The temperature only goes up to 20 degrees below boiling. So you could touch it. It won't feel good, but it's not going to kill you. Might burn you a little, but this is really not, you know, that's going to really hurt you.
Of the iron and the base of the water, that
it actually has something to do with that, but that's not really, because if you look at the chart, you could see what it is for water as a I don't have.
It looks like liquids have a higher.
They do, and I'll tell you that some of what that. Yeah, I mean, it's really a topic for next semester, but it's because of the interactions between water molecules. And when you put heat into it, it allows water molecules to separate, to pull away from their neighboring molecules, which requires energy. And so that's what the energy goes into. And iron, all it is these iron atoms next to each other, and all they could do is vibrate in place. That's all they can do. It can't do anything else. And so they can't separate. So it's just this energy all goes into moving around, and motion energy just causes the temperature to go up. So anyway, so there's a big difference in specific heats between these two things. All right, so what is this useful for? Well, for us, we would like to be able to, I guess I'll have to maybe do this next time, but I just want to set the stage for this problem, okay? So we have a chemical reaction. Suppose we want to figure out what is the delta H for reacting 1 mole of aluminum in this reaction here. And maybe you've noticed I put a fractional coefficient on the H2. I did that because I wanted to keep a 1 here on the aluminum, because I want to be able to figure out the delta H per 1 mole of aluminum. So what's in the soup over here, I wouldn't want to have a sip of it because it's hydrochloric acid, 100 milliliters. And it's a piece of aluminum that's 0.125 grams that's been dumped in there. And the temperature starts out like over here, and it goes up to some final temperature. So it's heated up all the water and all the reaction mixture from the initial to the final temperature. And from that change in temperature here, we can multiply that change in temperature by the mass of the solution and the specific heat of the solution, which is pretty close to what it is for water. So we know what that is. And we'll get a Q, and that will be equal to the delta H, except not quite, because we'll have to change the sign, because we know that this has to come out negative. So I'll go over that with you next time, but that's the stage for, that's what a calorimetry problem does. Okay, I'll see you next time.
you're given this because I'm taking physics also.
Oh yeah, are you doing any of this stuff?
Kind of around, that's why I'm asking for many questions, because I kind of get it a little bit.
Good.
Yeah, I know.
So this is the thing that we have to turn in today, right?
No. No, that was due last week. Oh no, this was never due. Because the practice problems 1 through 5. No, these I have the answers already posted.
I have an old batch from before that I never got from you.
There you go. I gave it to you.
Thank you, dear. Oh, one is for me.
Sylvia.
You, Sylvia? Yeah. Here's your document. I'll give it to you. Yeah. Tomorrow, I got the quote. Yeah.
Yeah.
Yeah. And then have a lot. Well, no, I think we should. Because I wanted to know where the, it's fine, I don't have to, but I don't know how. I want to know. What are you gonna do? Was there no problem?
Oh my God. Oh, yeah.
Yeah, it'll be better.
Yeah, but I don't have it.
What was it about?
I corrected labels that you make us notice. Thank you.
You're welcome.
So it's not an oxidation number.
What about oxidation number?
I corrected your oxidation number was wrong.
Oh, really?
Taking back number.
Oh, yeah, right. I remember that. Oh my God, I'm only good on one side. Oh, Miles. All right, great. Thank you. No, thanks for correcting me. Oh,